I'm just going to start off with a very serious take on reinforcement learning. Actually, maybe before I even do that, let me just start with a very quick informal poll. How many people are using reinforcement learning in their work? So, okay, I think I see one hand. How many people have ever read a book on reinforcement learning? Okay, so a few people. Okay, so that was kind of my expectation. And this talk, you'll see, is mostly very introductory. So hopefully, you can walk away from this with some sense of at least what the topic is. I have a lot of code that's available for you to look at afterwards. But let me just start off with this very serious take on the topic. Oh, what is it?
Figure 8.
Incredible. That's 5 for 5. You can't see these, can you?
No.
You're not cheating me, are you?
No, I swear they're just coming to me.
Okay. Nervous?
Yes. I don't like this.
You only have 75 more to go. Okay? What's this one?
It's a couple of wavy lines.
Sorry. This isn't your lucky day.
Get a little tired of this.
You volunteered, didn't you? We're paying you, aren't we?
Yeah, but I didn't know you were going to be giving me electric shocks. What are you trying to prove here anyway?
I'm studying the effect of negative reinforcement on ESP ability.
The effect? I'll tell you what the effect is. It's pissing me off.
Well, then maybe my theory is correct.
You can keep the $5. I had it.
I will, mister.
So many of you are probably familiar with that scene from Ghostbusters. It's actually based on somewhat of a real experiment. And it brings up this question of negative reinforcement, and it's directly related to a lot of what we're going to talk about. So just to start with, the talk here is called In Search of Pi. Pi in reinforcement learning and in many fields is a policy that you're trying to learn. And that's the focus of what we're going to be looking for. We want to learn how to follow a policy to go from one state to another based on a set of actions. This idea of reinforcement learning is very, very old. You can really find it all the way back. I've just included 2 quotes here to give some sense of that. John Locke had an idea that was crucial to his philosophy, wherein there's some superpower that gives rewards and punishes, and based on that, people will kind of follow certain kinds of behavior. And in Alan Turing's famous essay where he introduced the Turing test, he also introduced this idea and talked about the total number of rewards and punishments applied. And that also is getting at a crucial aspect of reinforcement learning, because we're trying to get at an expectation of reward over time. So this is a very old idea. It's kind of coming into popularity again now. So this is the outline. I'm going to start off by putting reinforcement learning in some context against things that people have probably already seen. I'm going to look at some motivating examples for how it's being used. We're going to go through the very simplest example, which is an N-armed bandit. And a little plug for John Miles White, has a book on that, who's also from this meetup. Then we're going to look at different models of reinforcement learning problems. We'll go through different methods for solving those models. I'll walk through some open source code that's available for doing this. And then I'll give some references so you can dig into it a little deeper. Okay, so starting off with some context. So just first of all, the show of hands in here is not overly surprising. This is from a recent post in the machine learning subreddit. And it said, why is reinforcement learning so rare here? And many of the comments were pretty derogatory. But my basic take on this is that I think reinforcement learning is kind of underappreciated within our community. The purpose of it is to optimize over some long-term behavior. And that's something that doesn't easily fall out of other kinds of models. It's good for handling complex environments. And also, it provides a framework for working with streaming data, which is becoming increasingly important. And we recently had a talk on that topic. Machine learning as a field is usually kind of separated into these three different categories. And my guess is that people are very familiar with the first two. So in supervised learning, you have examples that that are labeled, and you're trying to fit a model from a set of features to figure out what those labels are. In unsupervised learning, you have unlabeled data, and you're trying to find if there's some kind of pattern to it. Reinforcement learning is sometimes thought of as being kind of like supervised learning. You're given a set of states and actions, and from there you're going to try to learn some function. But hopefully, you'll see as we go along, it's actually fairly different. So there are different kinds of views of how these things relate, and I think at a basic level they are actually quite different. A slightly more nuanced view would say that they're actually fairly strongly related. There are ways in which each of these different branches of machine learning are used. So I've kind of put at the center this idea of active learning, and that's really where you get all three different forms of machine learning coming together. I don't know if anyone has ever used active learning, but it's also an interesting field. So there are, clear relationships between these things. And there's also another view, which is even more complicated, but which basically looks at the complexity of the problem. And in this view, you have supervised learning kind of at the bottom left corner. It doesn't have any kind of sequential nature to it, and it also doesn't have any kind of reward structure. But as you add those features in, you get more complex problems. In the top quadrant, you have basically multi-armed bandits, which, again, maybe some of you are familiar with. And there you have a reward structure, but you don't have any kind of sequential nature to it. And then as you add in the sequential aspect, you get to reinforcement learning. And there are actually theories that allow you to go from reinforcement learning down to supervised learning using what are known as reductions. So again, there are a lot of intimate relationships between these different methods. So what is reinforcement learning? To start with, I just mentioned there's a really fantastic book. It's called Reinforcement Learning. It's by two researchers in the field, Richard Sutton and Andrew Barto. And I highly recommend this book. It's also available for free online. So definitely take a look at that. And a lot of what I talk about is, taken from here in some way. So one idea that they introduced at the very beginning is this idea of a system that wants something. Again, we're kind of getting into this idea of getting rewards, and we're trying to achieve a goal. So at a basic level, a reinforcement learning problem, you have an agent that's taking actions in an environment, and that environment may have some kind of uncertainty in it, and it's going to receive rewards as feedback from the environment. The goal is to find a policy that will take your state and give you an action. And you want to find a policy that will maximize your rewards over time. And it's very tightly related to ideas from psychology and animal learning. Incidentally, if there are questions at any point, please interrupt. Happy for this to be interactive. Yes?
Do you assume that the environment's stable through time?
That's a great question. So the question was, is the environment stable? There are kind of different ways of thinking about that. As with everything, there's nuance. There are ways of thinking about the environment as changing over time as well. Most of what I'm going to be talking about will be, there's uncertainty in the environment, but it's stable. So this is kind of a model for how the problem is structured. So there's an agent, and that agent takes actions against some environment. And the environment then gives feedback in terms of an updated state and reward. So we're always going to be kind of following this model. As I mentioned, this is used in a lot of different areas. Most popularly, I would say, within artificial intelligence, particularly robotics. It's very popular there. And I'll walk through some examples of robotics where it's being used. Control theory and optimal control. I don't know if anyone here is involved in that area, but sequential decision theory. And there's also this idea, which I've listed at the bottom, approximate dynamic programming. Approximate dynamic programming is basically another word for reinforcement learning. They're kind of, what we found over time is that this exact set of ideas has sprung up in different fields at the same time. And that's great because it shows how powerful these ideas are, but it also has led to a problem of different notations, which I'll comment on as well. And then within neuroscience, reinforcement learning ideas have been very powerful at explaining how dopamine operates in the brain, and so that's a big active area of research. And in psychology as well, how people learn based on interacting with an environment, there's been a lot of study in that area. And again, if you look, this was a survey done by Kazba Sevzari, and what you can see, he did a survey of how often reinforcement learning shows up in papers. And it actually is occurring around a lot of different fields. So, a lot of places where you see these applications are in AI and robotics, but it turns out that it's really being used very broadly if you think about it in a broad way. Just from an AI perspective, I'm sure many of you have seen this textbook. It's the most popular textbook for AI. And if you look at kind of where reinforcement learning fits within the field of AI, if you just take, this is kind of the classic approach. They work through kind of search algorithms at the beginning of their textbook, basically. And so in search algorithms, you're thinking about, I have a state space, and I'm going to search out throughout that entire space. And as they get more and more complex problems, they get to this topic of sequential decisions. And we're going to talk about the ideas in sequential decisions, which include MDP, which is Markov decision process, and it also gets into game theory. And then later on, several chapters later, they get into the topic of reinforcement learning. So the difference between reinforcement learning and sequential decisions, if anyone's seen sequential decisions before, is really that reinforcement learning has even less structure to it. It has less of a model of the environment than in a typical kind of operations research or sequential decision setting. These are some of the kind of major considerations and areas where people are doing research right now. Some of this kind of applies broadly to all different areas of learning, but generalization is a big problem in reinforcement learning. With a lot of reinforcement learning, they end up running into the curse of dimensionality. It's a huge issue because you're trying to basically search through a huge state space. You have all these states and actions, and you need to figure out how can you find the optimal behavior. But then you're running up against this problem. If I'm searching through all this state space, I have to shrink that state space down. And then if I get into a different setting that I've never seen before, how can I generalize from that? So that's a big area of research, and that's where people are combining ideas of supervised learning with reinforcement learning. I'll comment on that. Sequential decisions is kind of unique to this topic. So here, we've got a model of the environment, and now we want to know, okay, given this model of the environment, how am I going to act? And that's where we get into this planning problem. Related to that is this idea of exploration versus exploitation. And I mentioned this multi-armed bandit problem, which I'll go through in a little more detail. But the issue is, if you're searching through this space and you're learning different ways of acting, and you're getting rewards, and as you continue to do that, there's some cost to searching. So at what point do you say, okay, I've searched enough, I have a good policy, and I should start to exploit that? So there's this tug of war between how much do I continue to search and how much do I start to act? And then another big area, again, these are very high dimensional problems. So convergence, given these big state spaces and these algorithms, how can we actually confirm that we've reached the optimal point? And these are potentially very complex problems. So there are a lot of cutting edge research now that's trying to prove that certain kinds of algorithms converge. And there's been a lot of success recently within the last few years on that. I'll just comment briefly on the kinds of different flavors of this problem. So they vary in terms of the kinds of uncertainty. For instance, am I able to know what state I'm in or not? Can I know what action to expect or not? Whether there are multiple people involved. So, one classic setting for reinforcement learning is in game playing. And in there, you may have two people who are playing and they're adversarial. So you have to think about, if I act a certain way, how is that person going to act? And that gets into these multi-decision maker problems. There are two very different ways of formulating the problem, either as model-based or model-free. I'll go through that as well. Right now, people are really more focused on the model-based version of that, which seems kind of counterintuitive. I think within supervised learning, we like to think of model-free learning as being fantastic, because you're not imposing your structure on the problem. But model-based learning also has a lot of benefits. Particularly, it's able to learn much more quickly. And then, basically the complexity of the problem is the state space discrete or is infinite? Is it continuous time or discrete time, and so forth? And as we make our problem more and more complex, the approach to solving it becomes more and more complex. So all of these decisions are very important when you characterize a problem. I mentioned Richard Sutton. In many ways, he's kind of the father of the field. And he recently gave a talk trying to characterize what are the main ideas behind reinforcement learning. And he chose these four. So I'm just going to comment on them quickly, and then I'm going to go through more detailed examples of each. But the first one he thought about was that there's a time aspect to it. In many supervised learning problems, we could just kind of throw time out of the equation, right? We just say, given a certain set of features or states, what do I expect? Here we're actually thinking about things taking place over some period of the life of an agent. So the time aspect of it is very important and potentially somewhat unique to this. The second one he listed was reward or value. And here I think one important idea behind this is that we're thinking about things in a very long-term way. So when you come up with a supervised learning model, you're saying, I'm sitting here in this current situation. I have this set of features that are such and such a way. It tells me to do this thing. In this setting, we may not always follow that, because doing things in a supervised learning setting is very greedy. So you're always thinking, what's the optimal thing to do right now? But what we really want to think about is, what should I do in the long run? And that's where this idea of value, I want to think about things over some long period of time. Sampling is very important and has helped to deal with the problem of dimensionality. So in classical kind of AI search problems, you've got this big state space and you're basically searching the whole thing. That's kind of the very basic idea. But if one of the key ideas kind of leading into reinforcement learning was, let's use Monte Carlo methods. So rather than searching the entire state space, I'm going to go down one track now, and I'll try another one, and I'm going to sample over the whole space. And that's led to a lot of kind of improvements in convergence. And then bootstrapping is the idea that basically I've got an estimate of value right now, and I'm going to update my belief of that value based on what happens next. So you're using your existing knowledge of the world to kind of continue to improve your updates. And again, that helps both in terms of kind of improving convergence, but also in terms of getting better estimates. Okay, so let me just quickly go through a few examples of how this is being used. So kind of the classic example is the Skinner box, right? I'm sure many of you are familiar with this, but the psychological experiment from the 20s, and it was really foundational in terms of psychology. They were looking at rats who were touching levers, and they would get rewards under certain settings, and they were able to kind of model how did the rats respond to reward. And that, again, there's this tight relationship between psychology research and reinforcement learning. And I recently noticed there's actually kind of, and it'll be interesting to see how this takes off, but it's kind of a human version of this now. So there's a device you can buy called a padlock, and it literally will shock you if you don't behave well. So I could see maybe Apple Watch version 2 will have this feature as well. But it's a powerful idea. Another very classic example, and again, this is really getting into dynamic programming, but dynamic programming, many of you may be familiar with that. That's really foundational in terms of reinforcement learning. So there's the traveling salesman problem. It's probably one of the most well-known computer science problems. The dynamic programming from Richard Bellman was able to solve it more efficiently than other algorithms prior. So it was a really big leap forward in terms of solving shortest path kind of problems. So it's, again, very foundational for computer science. Probably the most well-known reinforcement learning problem comes from games. So there was this problem, it was called TD Gammon, and a researcher at IBM fit a model using ideas called temporal difference learning, which I'm going to go through. And he fit it using a neural network. So again, you get this kind of intermittent relationship between reinforcement learning ideas and supervised learning. You're combining a model from supervised learning with this kind of behavior over time. And that's where you get a lot of power. And he was able to beat all of the world's grandmasters using this program. So it was a huge leap forward in terms of computers and games when this came out. And you know, a lot of people look at this particular problem where he was playing backgammon, and they've studied it and they've said, you know, this is kind of the epitome of reinforcement learning. We're not going to go anywhere from here. And there hasn't been a lot of coverage, I would say, of the topic since this. In particular, there wasn't much success in games like chess. There wasn't, you know, particularly another game that's very popular is a game called Go. And I don't know how many of you play this, but it's a very complicated game. There's a lot of thinking that Go would never be solved by a computer. It's a very complex game. So in Go, you have an enormous number of states. So in terms of this kind of cursive dimensionality problem, it's very, very difficult. Now, this is kind of getting into this idea of having what's called function approximation. So again, you're combining ideas from supervised learning with ideas from reinforcement learning. And by doing this, they've made recent major breakthroughs in the field of Go. So, you know, when they started introducing this sampling approach to the game, you can see initially they were looking primarily, this blue line is kind of classic search problems. These are classic AI search algorithms to solve the game of Go. And then they started looking at using a sample-based approach. And ever since they started taking that approach, the y-axis here shows a measure of how successful the game player is. And they actually started to beat the world grandmasters at this level. Prior to that, they were kind of, you know, anyone in this room could have beaten them. They were very simple programs. So again, kind of getting into this idea of function approximation. And in this case, this is using gradient descent methods. But that's made major leap forwards in this field in the last few years. And then just one last very quick example. Many of you may be familiar with this as well. But Andrew Aaron from Stanford was able to train remote controlled helicopters. And again, this is with these helicopters. Basically, in theory, having no idea what to do prior to being trained. So you're not giving any examples of, you know, you should make a left turn in this setting, or, you know, given the wind in this condition, you should make a right turn. That would be more kind of a supervised learning problem. But they introduced a simulator, and they were able to completely train these helicopters to do aerial stunts. And again, this is, I think, in 2005. And they were doing some extremely difficult maneuvers. Most helicopter pilots could never do these kind of things. And again, this is all completely trained without any feedback. So that's, again, another very well-known, popular example. Okay, so let me just go briefly into what I would call the simplest example, which is the multi-arm bandit. So many of you, again, may be familiar with the multi-arm bandit. John Laws White has written a book about it. And in terms of reinforcement learning, you can think of that as being a reinforcement learning problem with one state. Mostly what we're thinking about here are sequential decisions. I've got multiple states and I'm acting over some sequence of events. In this problem, you only have one state. So in the multi-arm bandit problem, a one-arm bandit is basically a slot machine, you can think of it that way. And you have, say, a number of slot machines that you can pick from. So you can, let's say you walk into a casino, you don't know which one is going to pay off. You have this row of slot machines. You want to figure out which one is going to pay off the most. So this gives you a set of routines that you can follow to pick a machine, basically. So you have a set of actions you can take, and in this case, those actions would be machine one arm, machine two arm, etc. And you can choose which one you want to pick. Every time you pull on a slot machine, it may pay off or it may not. There's some probability distribution to that. And then over time, there's this idea again of value. So we're not just interested in, did this machine pay off right now? We're interested in, over time, how much did it pay? So this, many people will probably be familiar with this XKCD comic, which is really directly related to this problem. So you can think of, again, someone walking in and pulling on that lever. In this case, they have very dire consequences, right? It's not that they didn't just win the slot machine. So most people, when they're in this circumstance, they take that negative feedback and they would probably quit, right? But, so what would a normal person do? They'd say, don't do that again, right? But of course, the scientist wants to know, is that really what's going to happen every time? So they keep doing it. So you can think of our reinforcement learning problem the same way. If you just simply took that negative feedback and never pulled that lever again, then you wouldn't learn, right? So we have to keep experimenting, and that gets into this exploration versus exploitation trade-off. So I'll just briefly describe kind of the most basic version of this, which is called epsilon greedy. And there are many, many other versions of this. There are issues with this one, but it's simple to explain. So let's say you have some idea. You keep testing these different slot machines, and you figure out, okay, this one paid off. That would be your best arm. So you have some notion of what's your best arm right now. That's your belief of the maximum value if I keep pulling that one. But periodically, you'll go and you'll say, okay, you know what? It's time to go test the other ones. There's this parameter epsilon, and you can set that to be any number you want. Let's say you set it to be 0.1, which for whatever reason, a popular choice. Then that would say 10% of the time I'm going to go out and randomly test all the other machines. And then the rest of the time I'm going to go use the machine that I think is the best. And by having this kind of policy, you end up being able to converge on the best machine. And this is kind of a popular mechanism for our website optimization. So again, some of you may be in this field, but you want to know if I put a certain ad on a certain page, will people click on it, and will I get that reward? So you want to be able to, typically people think about A/B tests. This is kind of an extension of that. So that gets into, again, this exploration versus exploitation trade-off. How can I be sure that I'm going to explore as much as I need to and come up with the optimal solution? Okay, so let me just go through some models now. And I'm going to focus on a problem called the Markov decision process, but I'll try to put it in some context. Yes?
Isn't there a principled way to choose epsilon?
I'm sorry?
Isn't there like a way to choose like an optimal value of epsilon?
Yeah, there is. And I mean, again, I don't know how many people even use epsilon greedy now. There are other methods like upper confidence bound and Bayesian methods, I think, are more popular. And another thing, I think most people would do like a decreasing epsilon, for instance. You wouldn't necessarily set a value and just stick to that, but you would, over time, migrate. Yeah. Okay. So just to start with, I want to put this again in a little bit of context. So many of you will be familiar with Bayesian networks as a way of kind of explaining a probabilistic model. So in a Bayesian network, we would typically have states. there's another form of network which extends this that has two additional nodes. A decision node, which is like an action, and a utility node, which is a reward. And I'm just going to stick to Markov models here, but many people will have looked at Markov Chains before. This is a very popular time series model. In Markov Chains, we assume that all the states we see are observable, and also that we have no control over transitions. So they happen with some probability. You go from one state to another. So we can kind of extend this idea down further. Markov decision process, what we're going to mostly focus on, the states are observable, meaning if I'm a robot, I know where I'm located, and I have control over what I'm doing. So I can turn right, I can turn left, and so forth, and I know what I'm doing. In the kind of time series sense, a hidden Markov model extends the Markov chain by saying that the states that we're in are not observable. Okay, so that becomes a powerful idea. And in the reinforcement learning setting, you can have the same idea, which is called a POMDP, which is for partially observable Markov decision process. And again, as you make these things more complex, the solution methods become much more complex. So most people have tended to focus on Markov decision processes, even though POMDPs are very popular now, and in part because if you think about certain kinds of problems, like robots, for instance, how do robots know where they're located? They have sensors, and those sensor readings are always noisy. And not only are they noisy, but to get a good reading, you need a more expensive sensor. So if you can model things as kind of unknown states and learn from it in that way, you can actually not only make problems more easy to deal with, but you can also make them more easy to implement. So Markov processes. The Markov property itself, which again is kind of important to all of this, is just that the probability of the next state is only dependent on the prior state, or the existing state. So it doesn't matter all of the information that came before a given state transition. All that matters is where I am right now. And this particular topic is also, you could go into a lot of detail on, like for instance, how do you define a state? You can define states in very complex ways that would include prior information, for instance. Right? So the whole subject of defining the state is in and of itself a very complicated question. But this is the simple idea, just that we're only going to, in order to know what happens next, all we need to know is where we are right now. Okay. So the Markov decision process adds these two additional features, right? I'm in a state, I can take an action, and when I take that action, I receive a reward, and then I transition to the next state. So that's going to kind of fully define the reinforcement learning problem. Hidden Markov models have also become quite popular in the past few years. And in this case, there's a hidden state. So you don't know what the state is, you just know some observation of that state. And then you need to try to figure out what the state is based on the observations that you have. So you basically have a belief of what that state is. And then partially observable Markov decision processes, which are the extension of Markov decision processes, introduce the same idea. So rather than knowing what state I'm in, I see some observation, and then I have a belief of what state I'm in. So again, you've got this kind of extension to the problem. Okay, so let's define the reinforcement learning problem explicitly now. In the reinforcement learning problem, we have a set of states, and those states could be continuous or discrete. In most cases, people try to either have discrete states, or they'll try to discretize the states, because if they're continuous, then it makes the problem potentially significantly more challenging. You also have a set of actions that you can take. So again, you could think about, maybe I'm a robot. I can go north, I can go west, east, and so forth. And again, typically that's seen as discrete, but it could be continuous. And then you have some reward that you get for being in a state. So I move into a certain state and I get a reward. That reward could be 0. And that's actually a very important idea as well. And in addition to that, we have some probability distribution given a state and action that I'm going to transition into the next state. And a lot of people also introduce a discounting factor because they don't want to have to keep learning forever, basically. This discounting factor will give more or less weight to the most recent observations. And the objective, really, that we're looking for here is to find a policy. And the policy is just some function that says, given that I'm in a given state, again, that state could be any complicated thing. It could be, the sky is blue and I'm outside and I have my umbrella in my hand, or whatever it is. It could be any different set of features. And given that I'm in this state, what action should I take? So how are we going to learn what a policy is that we should take? So the way we're going to do that is, I'm going from one state to another. And every time I transition from one state into another, I'm going to receive a reward. And over time, I'm going to build up this idea of value. In operations research, they refer to it as utility. But really what we're looking for is, what's the expectation of reward for being in a given state? And the way we end up implementing this is using something called the Bellman equation. So virtually all reinforcement learning problems are put in the same way, that the value of being in a state and following a certain policy is that I get a reward for being in that state, and then I get, from there, every subsequent reward. So here you're getting kind of a very powerful idea. I'm breaking off what's happening right now versus what's going to happen in the future. And this part of it here is kind of an estimate, right? And another thing that I just want to highlight here is that this is for a given policy. So any given policy could be optimal or not. But you can still kind of dictate what's the value of following a certain policy. And over time, when we know values for every policy, then we can kind of start to say, what's the optimal one? Another important equation that I'm just going to put here is this Q function. So rather than simply talking about what's the value of being in this current state, we can talk about what's the value of being in this state and taking an action. And the difference between these two equations may not be all that readily apparent. I mean, it's really just the introduction of this A. And why would we really care about that? Well, it turns out that reformulating the problem in terms of this Q function allows us to solve things without having any knowledge of this function or this function. And that's really where we get into reinforcement learning versus kind of traditional operations research and dynamic programming. And incidentally, the difference between the Q and the V is this A. But if you take the max of all the Q's over all the A's, then you get V. So the value function is literally just the maximum of all the values that you could get for taking an action given a state. Okay, so let's just kind of think about through this problem a little bit, and we'll see kind of how things fall out. There is a canonical example that most people use, which is called Gridworld. Here I'm just showing a maze. But you can think, let's say I'm starting in a given position and I want to get to a certain goal. How could I formulate this problem? Now, I have no feedback to start with about what's the right direction to go given a current position. So I need to start kind of introducing some feedback into the equation. You might do that in different ways. One way would be to say, when I reach the goal state, I'm going to get a big reward. Another way to formulate the problem would be, when I'm not in the goal state, I'm going to get a punishment. Okay, so again, we're kind of getting into this Pavlov thing, right? I'm going to get shocked every time I'm not in the goal. So let's think about that, okay? If you were in this, any given state, and every time you're in a state, you get a -1 reward, say, then over time, you can kind of think about how that's going to work. It's going to sum up to some value. So let's say I'm in this state. To get from here out to here, if I'm collecting -1 rewards on each step, I'm going to end up with this value. And now if you just kind of take a look at this, which is just literally summing up these rewards at each point, and this is our value function, then you can easily just kind of look at it and say, okay, if I'm in this state here, which would be the best way to go? Okay, I mean, based on these values, this number is less negative, right? So this would be the way to go. And you can continue that process, and that's how we go from having a sense of value, I'm in a given state and I have a certain value from it, to a policy. So if we're able to learn this value function, then we can go from there to having a policy. And a policy literally just says, I'm in a given position, I have a certain value expectation, so I'm going to take a certain action. I mentioned earlier that one of the key ideas behind reinforcement learning versus kind of traditional operations research and dynamic programming is that in reinforcement learning, we don't have the full model of the environment. And what I mean by that is, if I'm in a given state and I'm going to move into another state, I don't know, first of all, initially, what reward I'm going to get. And second of all, I don't know what the probability of me moving into that state is. So what we're saying there is that in a reinforcement learning problem, I don't know what this function is, and I don't know what this function is. And so there are kind of two approaches to this problem. One approach says, let me learn what those functions are. And the other approach says, who cares what those functions are? Let me just find out what the best policy is. Okay, and I'll go through how those two approaches work. And as an aside, I mentioned earlier, this has kind of grown up in different fields. Again, some of you may be from operations research. In operations research, there's just a different notation. Not only is there a different notation, but actually they think about it in kind of the negative way. So in reinforcement learning, you know, we're very positive people, and we have a positive value function. In operations research, they're very negative people, and so their cost to go function, J, is literally just the negative of this. So they're trying to minimize a cost, or we're trying to maximize a utility. Okay, so let me just go through. We've kind of defined what this problem is, right? We have this setup. We have action states or rewards, and we have transitions. And now the question is, how can I learn how to do this? Okay. So I'm just going to go through what all the kind of major ways of solving these problems are, and then I'll briefly go through kind of some of the software that exists for doing that. So I mentioned this a little bit earlier, but this picture from Michael Littman, and Michael Littman, by the way, just as an aside, is offering a reinforcement learning class through Udacity. So I don't know, some of you may have seen this. If you're looking to kind of dig into this a little further, he has a course on Udacity, which is quite good. And it goes into a lot more detail on game theory than I'm going to cover. So it's also interesting in that sense. But there are kind of three fairly distinct approaches to how to solve these problems. What we're trying to learn here is this policy. So I'm in a state and I want to know what action to take. And this is really what we want to learn. There are methods that simply just try to learn that. Okay, so forget about all of these issues of value and transition probability and so forth. Let me just try different paths and search over the path space, basically. So there are some approaches that are very direct. They just try to learn this thing directly, and these are called policy search. There are other methods that I'm mostly going to focus on, which try to learn, given a state and an action, what's the value. And once you know the value, you can go from the value to learning what the policy is. So it's slightly less direct at getting what we really want. But then there's the other extreme, which says, rather than trying to learn a value to learn a policy, let me learn this transition probability, and let me learn the reward function. And this is kind of interesting, and this is where a lot of research is being done now. This is called model-based reinforcement learning. And this is kind of like a supervised learning problem. I have these different pairs of data, and I'm learning these functions. So this is very indirect. In this case, we're learning about the environment itself. So we're learning how the environment operates, and we're learning that in order to dictate what the value is, and then to dictate what the policy is. And there are benefits to all of these methods, and they're being used in different ways. For instance, policy search requires less memory. It's a little more direct. So some robotics are using those methods. Model-based learning can do a lot of simulating. So basically you're learning about the environment, And then you can do kind of Monte Carlo simulation over and over and over again, and you can improve your updates based on the simulation. So this approach is able to converge much more quickly, but it may not be as easy to implement as this. So in order to describe these different methods, I'm going to use yet another diagram. So this is called a backup diagram. Now in reinforcement learning, this idea of backing up information from the future is very, very important. So the way this backup diagram works is you get a picture of how the method for solving the problem operates. You're in a given state, and you're taking a given action, and that's going to move you into another state. And given that other state, you're also receiving a reward at the same time. Okay, so this particular picture that I put up here corresponds to dynamic programming. In dynamic programming, you are stepping forward one step, typically, and you're also, excuse me, you're trying every combination, basically, of actions and states. So you're doing a full lookup every time. And again, this is an idea that's been around since the 50s, and it requires a lot more information. Okay, so dynamic programming, many of you may have either seen or heard about. There are two basic methods for solving it. The first is, that I'm going to mention is value iteration, and that was introduced by Richard Bellman and when he introduced this whole problem to begin with in terms of dynamic programming. One issue to do with dynamic programming is that you need to know what this is, and you need to know what this is. So again, you will see dynamic programming in other fields. It's kind of less applicable in reinforcement learning, because typically we're thinking about issues where we don't know those functions. The other method is called policy iteration, and that was introduced in 1960. These methods are slightly different. The policy iteration one I just want to kind of drill into a little bit further. And there's this idea of generalized policy iteration. And this idea is kind of used throughout all of reinforcement learning. We can generalize the problem in this way, right? Basically, what we want to do is evaluate to learn this optimal value function. And then we want to use our updates of values to improve our policy. And there's this feedback between the two. So, I've kind of gone through this a little bit already, but we've kind of separated this problem into learning a value function and then updating a policy. And that gets into this idea of generalized policy iteration that you see over and over again, even in all these different methods. So the next kind of method that came up was using Monte Carlo. And this is fairly different than dynamic programming. In this case, we're sampling from the state space. And every time we sample, we're going to go all the way to some terminal state. And by doing that over and over and over again, we can kind of learn about the environment. But you'll see what's different about this diagram than this one. In this case, we're going through all the states, one level. In this case, we're only going through one policy. So we're going to go all the way to the end, following one path. We're going to learn about it. Following on that, this is kind of one of the key ideas in reinforcement learning is called temporal difference learning. And this was introduced, really kind of formalized in the 80s, but some of you, particularly from an AI background, may be familiar with Samuel's paper where he looked at checkers in the 40s. So this idea has been around, again, for a very long time. And basically what the idea in temporal difference learning is, this backup diagram, you'll see the difference between this one and this one is really, we're only going forward one step. And every time we do that, we're looking at what changed, basically. So if we look at this equation, I've got some expectation of value, and I'm going to update that given my existing expectation of value plus some additional thing. And I think I had that. So this alpha is called the learning rate. So given what the next reward is, plus what changed, okay, that's how I'm going to update my expectation of value. And this is a very powerful idea, just looking forward one step and kind of looking at how my expectation has changed.
Sorry, can you elaborate on the idea of what's changed?
Of what changed? Yeah, again, I mean, these things are very probabilistic, right? So when I transition from one state to the next, The reward you receive may be different. Where you end up may be different. And so I have some expectation of what, so there's that aspect. There's also the aspect that you haven't searched the whole state space, right? So what's my expectation if we go back to this earlier example? Let's say we've gone through this thing one time. And again, there's this probabilistic aspect. If I'm only looking forward one step and I'm in this state, and let's say I'm receiving -1 reward every time, then my expectation of what the value of this state is only going to be based on this one transition, right? So you're kind of walking forward in space, but you're only learning from one step at a time. And what about the next time I revisit this state? Let's say, you know, I continue in this process. I'm going from one state to another. I'm learning what's happening every time. Over time, there's this backup process that happens. So eventually, let's say I reach the goal. And maybe when you reach that goal, you receive some reward. Well, that reward is going to slowly kind of propagate its way back. As you step through, you've got some expectation of value in each state. And then as you go on to the next one, that value from the goal state is going to work its way back. And eventually, you'll converge on what the real value of that state is. So does that answer your question? So what's changing over time is really not the value of that state per se in this problem, but really our understanding of what the value is. So all these V's here, you know, could have hats over them, maybe like in a probabilistic setting. These are our estimates of value. And you're updating your estimate as you walk through space and sample the state space. So we're running pretty long on time, and I just want to get through a few more things. And incidentally, this presentation is hopefully fairly comprehensive, and I will be making it available afterwards, obviously. So, you know, and if you have questions at any point, don't hesitate to reach out to me. There are really two temporal difference learning methods that are very, very popular. I just want to touch on kind of what the difference between them is. So Q-learning is one. And in Q-learning, it's known as a model-free method. This was, you know, from the late 80s. And what that means is that in Q-learning, you separate the policy you're going to follow from the issue of discovering your value. I mentioned earlier there's a separate formulation of value and Q. Q is the value for being in a state and taking an action. And we're able to learn that function much more easily. And one reason why Q-learning is very important, incidentally, is that people were able to show convergence in it relatively quickly. And the reason they were able to do that was because of this model-free aspect, that it separated the value learning part from the policy. Sarsa is another popular method, and in this case, the policy learning part of it is integrated into the value learning part. So you're learning a policy and a value at the same time. And when you do that, you end up with different kinds of behavior. For instance, in a given robotic kind of problem, let's say your robot is walking along a cliff. In Sarsa, the robot tends to be very conservative. It will stay as far away from the cliff as possible. In Q-learning, because it's independently learning the policy and the value, it tends to be more aggressive. Basically, if you just kind of formulate these problems similarly. And it will walk right next to the cliff. So, you know, again, which method you choose kind of somewhat depends on the scope of your problem. And then the last kind of key idea is this idea of backing up by estimates. And this gets into a notion called eligibility traces. So the temporal difference algorithm that I just showed you a minute ago was looking forward one step. Well, what if we, and then if you go over to Monte Carlo, that's looking forward all the way to the end, right? But in actual fact, we can kind of parameterize this to go anywhere in between. And it turns out that if we do that, we go any number of steps, we can both speed up the problem and we can also get more accurate results. So I'm just including this picture here as an example. Lambda is this number of steps that we're going to take. When I mentioned earlier that example of TD Gammon, where they learned backgammon. That was an exact example of this. They were looking for multiple steps, and it turns out that if you set this lambda value to something other than 0, 0 being kind of a classical TD case, and not 1 either. 1 would give you fully Monte Carlo. But if you parameterize this somewhere in between, you end up being able to get a better model out of it. So combining all these ideas together is very powerful, and also it kind of unifies the field. So this is something that people have been kind of looking at recently, which is just taking these ideas of eligibility traces, being able to go multiple steps at a time while still sampling. It gives you very powerful models. And so you have kind of these different methods that I've described. Dynamic programming is kind of the most widely used, I guess, simplest form of it. You have temporal difference learning. And the difference between these two, you can see is kind of how far are you going to search on each step. And on the other hand, you have this idea of how many steps am I going to go? And that's where you get into this lambda parameter. And there you go from kind of a classic AI search problem all the way down to Monte Carlo. And so you have this space of approaches, and they kind of get unified by having this bootstrapping parameter lambda. Okay. Yes?
The last slide, where would you put A star?
Yeah, that would definitely be up here, kind of in this region. And that, by the way, is a very popular method still as well. I mean, I'm sure it just kind of depends on the problem. The benefit of, one of the key benefits of the ideas we're talking about here is first of all, it samples. It doesn't try to search throughout the whole space. And then it also has this idea of bootstrapping. So, kind of going back to the very beginning, not only are you going to be searching throughout space, but every time you search throughout space, I'm going to update my current belief of my state based on my prior, basically. So it's almost like a Bayesian idea. Okay, so let me just briefly touch on kind of code that you can use to work on these problems. And then I'll open it up for questions. Okay, so I think one of the key reasons why there are very few hands in here at the very beginning is because it's very hard to do reinforcement learning. And one aspect of that is that it's not available really in any widely used data analysis software. And most of the time when people want to do a reinforcement learning problem, they kind of tailor the problem, or they tailor the solution explicitly to the problem. And we all know from doing supervised learning that when you introduce your domain knowledge into the problem, you almost always get a better solution, right? Just having black box algorithms never works as well as having some prior knowledge to be able to at least structure your features and so forth. So, it's not overly surprising that you should need to structure these things, but in the current state of affairs, reinforcement learning problems tend to be hard to implement. So I've listed a number of kind of the most complete pieces of software for this. And I just really want to dig mostly into this first one. So RL-Glue is a library that came out a few years ago. And the idea is to abstract away the language. So RL-Glue is a server that sits in between different language interfaces. And a large portion of the reinforcement learning community is now using this. As another aside, there's a pseudo-annual competition. It doesn't happen every year, but it does happen some years, where they use RL-Glue. And so there's one actually just starting. So hopefully you'll all kind of run out after this meeting and go enter this competition. And it has some very interesting problems, including, it has a simulator directly rid of that helicopter problem that I was talking about before. And so what's amazing on some level is that with RL-Glue, you don't need to worry about what language you're working in. So I could write an environment, like a helicopter simulator, and you could write an agent that would try to optimize that helicopter. So RL-Glue is this server that just communicates through networks. Typically, and in fact, I I guess, always on the same machine. There was some discussion at one point about doing it kind of over the internet, and we're not doing that yet, but it provides a very clean structure to the reinforcement learning problem. So we have an agent that kind of will take those rewards and state updates, and it will try to learn what the policy is. You have an environment that's giving all that feedback, and then you have an experiment program that's kind of dictating what's happening over time. So RL-Glue has language interfaces for C, C++, Lisp, Java, MATLAB, and Python. And I'm pleased to announce that I created an R package for it too. And I'm going to work on a Julia one next. So what I would really love would be for there to be more of a community built around RL-Glue. And one of the really beautiful things about it, as I mentioned before, is that there are already a lot of environments written for it in other languages. So if you're not interested in writing a helicopter simulator, which many of you may not be, but you may be interested in kind of experimenting it with as a toy problem. And you can do that right now. I mentioned this is still, fairly early stages. I haven't posted it to CRAN yet, but I have implemented an interface for it. You can play with that, and I'll post some updates on my blog or on Twitter, some examples using it. On top of that, I'm also working on an R package that's going to implement a lot of the algorithms that I've talked about. And more than that, I'd also like to really make it implement a lot of kind of cutting edge methods. So I mentioned this eligibility traces. Some of these methods are really cutting edge. People are using these kind of in all kinds of different fields. So some part of this is already implemented. This is already implemented, and TD Lambda, I should say. And it sits on top of RL-Glue. So given these different methods for solving problems, you can interface with lots of different environments. And it also has different methods for solving, coming up with a policy. All right, I think we're pretty tight on time at this point. And yeah, this is basically how you would implement a model using this new R package. And I will send around code examples after the talk. So just to wrap up, some kind of further things for you to dig into if any of this has piqued your interest. I've mentioned the code for this talk is available on here. Actually, I may not have pushed it, but I'll do that when I get home. But it will be available here if it's not there right now. RL-Glue, the R package, is also on there. In terms of the community, there's a Google group that has a lot of kind of the key members of the community are on there. There's this RL community site, and I mentioned this competition earlier, so that's taking place. Here are some kind of survey literature that if you're not looking to read this whole book, but you are looking for 20 pages, then you could pick up some of these. If you're looking for a more general overview, Russell and Norvik is unfortunately very, very expensive, but fantastic. So I recommend it. Probabilistic Robotics is also a fantastic book. And this book here, unfortunately I didn't put the title, but I'll put it before I send it around, is available for free online and is also a fantastic resource and has reinforcement learning in it. And incidentally, I didn't include this in here, but if you're looking for machine learning books that talk about reinforcement learning, there are a couple there as well, including, I think, Tom Mitchell's book, excuse me, has a really nice, concise chapter on it. So some of you, again, may have read that book before. You might want to revisit it. In terms of reinforcement learning books, these are kind of the two classic references, and it's really fantastic, but Sutton and Bardo have released their book for free on their website, so definitely go on there. You can download it. This is also another book by one of Sutton's colleagues on algorithms that's also very good and is also free. These are some of the key people in the field. Again, this will be in the presentation. And that's the whole thing. So apologies, I hope I didn't put too many people to sleep here, but hopefully we have a couple of minutes for any questions, and if not, I will be going out for beers afterwards, so I'd love to get to chat with some of you. Okay, any questions? I guess. Thank you.
I have a question. Question? Like I say, you had alluded to the essentially the dependency of these problems on the definition of state, right?
Yes.
On how you define state.
How do you define state?
Okay. And in particular, my other concern in all of these techniques is because in some cases, let's say, if your definition of state doesn't comport with reality, right? I'm talking about, listen, when you're trying to control some physical plant, right? Like your model is not the plant, okay? And there are certain things, certain nonlinearities and things that are not in there.
Yeah.
Is there any way of dealing with fuzziness in state definition?
Is there any way of what?
Can you deal with fuzzy states?
Introducing kind of fuzziness. And okay, so the question was, it can be difficult to define states, and let's suppose that your state definition is either A, unknown, maybe you don't you don't know your state at all, or maybe you have some belief around your state. So yeah, there are absolutely ways to kind of go about that. As I mentioned, the less you know about the environment, the harder the problem. And the algorithms you have to use are harder. But the POMDP, that whole series of literature directly relates to there's some uncertainty in your state. So in that scenario, you basically have a belief about your state. So again, this is really kind of a Bayesian idea. There's some probabilistic distribution of what state you're in. And again, you could define your state however you want. But given that belief, every time you make an observation, you're going to kind of update that belief. So it definitely allows for uncertainty in the problem. I don't know, did that answer your question?
Yeah.
Or, yes?
Can you give a concrete example, maybe in your own work or some other work,
Yep.
of what kind of problem this can solve, and specifically speak about what is a state, how is a state defined, how do you figure out what the value is, how you define the value, and what actions your agent can take? So all of those, but a concrete example maybe in your own work,
Sure.
if you can.
Yeah. So I will give you an example kind of from my work area, I guess. There's a famous paper by Michael Kearns. Again, I don't know how many of you are familiar with him. He's at UPenn, and he's written a lot of important literature in this topic, but also in other areas. And he wrote a paper in 2005 that looked at what's known as the optimal execution problem. So this is kind of directly related to finance. And again, this is used in finance in some areas, but it's useful in any case when you've got some sequence of decisions you have to make and there's uncertainty, right? And you have a goal. So the optimal execution problem in finance is very well defined. You're given a certain number of shares of some stock to trade, say. So you're sitting as a trader, and someone says, execute 10,000 shares of Apple today. And your objective is to get the best price possible. So in the Michael Kearns paper, they set it up so that the state is, it's an interesting paper to look at because he gets into this state definition question. He could define the state as both, how many shares do I have left to execute? What is the order book? So, for anyone who's not familiar with trading and order book markets, there's an order book that says, there are a certain number of people who are willing to sell shares at a certain price, a certain number of people who are willing to buy shares at a certain price. Given how the order book looks right now, given how many shares I have left to trade, and he includes other variables that might be considered kind of more predictive. And his actions would be, at a given point in time, I'm going to sell some percentage of the shares or buy some percentage of the shares, however the problem was formulated. And the way he approaches the problem is again, this has a lot to do with you want to search throughout the state space in some way. So he creates a simulator of the market. So he has market data that he's replaying, and he replays it based on exchange rules that say, if I'm going to buy a certain number of shares, this is what's going to happen to the order book and so forth. So he simulates what would happen based on taking certain actions at given points in time, based on certain states, where a state is how much time I have left and so forth, and he's able to come up with optimal policies. And then he's able to compare that against, and in his particular paper, he didn't kind of compare it against well-established benchmarks, I guess, unfortunately, but he compared it against another kind of simple algorithm and showed that by introducing additional variables, he was able to get much better policies and so forth. So that's an example from finance. You can see, for instance, it's being used very widely in robotics. So I don't know exactly how Google cars are working, but if I had to take a guess, this is heavily involved, because what you're trying to do, and as I understand the Google car problem, is basically you have some model of the world, and they have, the way they're training their cars is not based on, like one way to do self-driving cars is to have one car to communicate with another. So I'm approaching a car, I can see that car, it's giving me lots of feedback, and I can kind of dictate how I should behave. Another way to do it would be to have some map of the world, basically, with immense detail, and then come up with these kinds of policies to say, given current state and so forth. So there's clearly a lot of training that goes into that kind of problem, and I presume they're using some methods that are at least tangentially related to this. There's certainly indications of that. Google recently acquired a company called DeepMind that some of you may have seen. And DeepMind's kind of big public thing was that, I'll include a reference to this also. They published a paper about learning Atari games, and it was all about reinforcement learning again. So a lot of these game problems where you have no prior expectation of, like, given a current state, I'm Mario and I'm in front of a pipe, what should I do? You just kind of, basically by trial and error, you go through the state space and you learn. Yeah.
The state space that you just mentioned, that was like a one-dimensional, one variable space, but I presume that most state spaces are multivariable. So.
Yeah.
And would they have some kind of a topology in order so that you don't have to treat separately every particular state?
So the question was, is there some kind of topology to the state space, basically, so I don't have to go through every state. So I kind of mentioned this a little bit, but the big problem in reinforcement, one big problem, I should say, is generalization. And the problem is you have all these states and actions, and you have this huge cursive dimensionality problem. So how can I possibly visit every state and every action? And in fact, in Q-learning, the convergence proof required that you visit every state and every action infinitely often. Okay, so I don't know how many of us have time for that. So a lot of the research that's gone into this recently is trying to generalize, and that gets into really using supervised learning methods to build a model of the environment. And in that case, you basically, you do end up with, you're fitting a model, like a functional form, to your state space. So you're trying to learn what model actually projects out this state space. That way, if I visited this state and I visited that state, but I never visited this one, I can generalize because I have a model of it. I don't know if that answers your question. Sorry, you had a question?
Yeah, could you apply this to like amateur online poker?
So the question was, can you apply it to amateur online poker? And I don't have any direct experience in that, but there are actually papers on poker using reinforcement learning. And in fact, they are interesting as well because they are looking at game theory. So in poker, you've got a multi-payer problem, and again, I could include some references there. I don't know how many people have actually applied these methods in online poker, but I imagine more than one. Yep. Oh, 1 minute. Okay, any last questions?
So what does a policy look like? Is it a bunch of features and an action, and then you produce a reward for it to be a regression?
So the question was, what does a policy look like? So in the classic methods that I kind of mostly showed here, they're basically tables. So you do a table lookup. You're in a state, and that table tells you to take a certain action. And again, in this kind of generalization, world, we can't do that because, you know, if a robot has some wind, all of a sudden it's in a state that it never simulated. Now it's going to fall off a cliff. So instead, we will basically, you know, like one very popular area is just literally linear function approximation. So you can run a regression, yeah, essentially saying, give it certain sets of values, expectations, what's my model of what action I should take. So you can come up with a policy as a function instead. Okay, I think, you know, if there are any more questions, you know, happy to take them either over email, on Twitter, or over beer. You know, thank you, everyone. Hopefully, you know, we'll go out and choose good policies from here on.